Okay, so the I²CNER seminar series was launched at 2010 upon the inception of I²CNER. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. So in this time, I am Motonori Watanabe, and I will be your host today. So today we welcome to Professor Shun-Wei Liu, Dr. Shun-Wei Liu from Michi Technology University. So he's also director of this of the center for related to the organic electronics and research research center. So this time, actually, I'm one of the maybe longer time with a colleague with you.
Yeah.
So and then we now collaboration with Shun-Wei related with the organic function of electronics. So therefore, this time he's a pioneer kinds of the like this of research at Taiwan. So therefore, I would like to invite to him at here. So today he and also before that, I'm sorry. So before we begin, I would like to take a moment to remind you that your question from online. So this time is a hybrid style.
Yeah.
So on-site is okay, you can raise your hand. But in the case of the online, if you have the question, in this case, could you please raise hand button online of the Zoom, and then or type of the question comment in Q&A box. Then we can pick up for you. So okay, this time it's the title is advancement in organic functional electronics, innovation in imaging and energy harvesting devices. Okay, Shun-Wei, microphone is for you.
Okay, yeah. I really thank my good friend, Professor Watanabe, invited me to give the short speech in I²CNER. Actually, last year, that's my first time to come to the I²CNER, and I feel that, this center is very tough and doing some, the energy evaluation of energy harvesting research in a Kyushu University. And I also visit the I²CNER core facility. That is very nice. So if I am a researcher, I will very happy working here. And in this time, I try to give the show the research topic and share out the research achievement. So in this time, for my talk, I will separate two parts. The first one part, I will mention that how to make the images. So that's a functional electronic, okay? So if you can try to integrate the individual components into the single electronic, you can make a very special applications. So that's my first one part. I call that's the functional electronic. And for my second part, I will talking about the energy harvesting. So I think that maybe the researcher or the postdoc fellows, you're looking for the energy harvesting. I want to talking about the very important concept. The light can become to the power. Even the weak light, we can become to the electricity. If we can do in these special things, we can try to drive in the microelectronic. So the light is a power, but you should know that how to convert the light to become to the power. Okay, so that's my second part, the talk. And before my talk, I try to briefly introduce our university. That is a Ming University of Technology. Actually, the Ming, that's a private university in Taiwan. But I can talk to you, this university is quite special because our founder, the Mr. Yongqing Wang, he's a very famous people in Taiwan. And he also building up a very huge group. That's the Formosa, the prestigious group. So this group including more than 50 or 60 companies. So you can imagine that we have the hospital, university, the petrochemical, and the DRAM. So the Formosa prestigious group, similar to the Japanese company, that's Sumitomo. So you can think about the one university we can get the full support from the Sumitomo. So that's a huge fundings. And until now, the Formosa prestigious group already get the ranking number 5 in the world for the petrochemical. Okay, so that's very important things. And if you check our university, the ranking for the THE, the review process, our university is not so big, only the 200 faculties. But we can get the research item, the review process, we can get a ranking within the 600 from the THE, the review. So we only have 200 faculty, but for these research items, we can get very nice score. Means that always we give the high pressure for our faculty or our employee. Okay, so like me, we only have the 15% of times can do in the pure research. Another one of times we need to service a company. For example, we need to transfer all the knowledge become to the final product and sort out in the market. So that's our vision. So that's why we can get a very nice ranking for the research for the THE to review the process, because we only have the 200 faculties, okay? So that's the different things. And for our location, that's very convenient for the guests. So if you have sometimes, I will try to invite you to visit our centers. So I checked the map. Actually, you can take the flight from the Fukan Airport to the TPE, that's a Taiwan Taoyuan Airport. So I checked the distance. It's not so far, okay? Just 103,000 kilometers. And the flight duration within 2 hours, you can come to the TPE. And in there, you can try to take the metro. So that's a very popular transportation. So from the TPE the airport, come to the A6, the Taishan-Guihe stations. So just within half hours, you can come to there. So the university just located nearby the A6 Taishan-Guihe station. Of course, you also can try to travel to the Taipei downtown. There you can find a very famous buildings. That's a Taipei 101. Okay, so from our university to the Taipei 101, still you just need a half hour, so you can come to there. So you can check this map. Actually, our university we just locate between the airport and the Taipei downtown. Okay, so that is a very nice location for you. And you also can try to travel from the Taipei to the Tainan. So this one is a Taiwan map. So the northern of the Taiwan in here, we just locate in here, right? The middle side is a Taichung, and the south side is Tainan. So if you take the high-speed rail from the Taipei to the Tainan, just within 2 hours, you can come to there. So if you have a choice, you can try to let me know, and I can arrange the academic tour or the sightseeing the tour for you. So that's my our university briefly the introduction. Okay, so I can talk to you. Our location is very nice, and from our university come back the Taoyuan airport. You just need the half hours. You can come back there. Okay. Okay, so for our centers, actually we're doing the functional electronic. But the special things we try to use in the different type of materials. For example, we have the small molecule materials, the polymer materials, and the perovskite materials. And actually, we also try to study different type of electronic, like the photodetector, the display, solar cells, or the sensors. And we also can make the functional, the electronic, like the images. So you can check this slide. We just briefly show you what is our research teams. Well, we get the very nice result. We try to study the perovskite LED. And this one, that is the images. So that's my first one to talk in the I²CNER. We want to teach you how to combine display and the sensors and the transparency electrode. If we can try to integrate these individual components into this single device, you can make these images. So what is the function for that? We can directly absorb the invisible light. Then we show you the visible emission. So that's a real-time imagery, the sensors. And we also have one team, they'll try to study the perovskite, the solar device, and the solar modules. And we also can prepare the high quality the perovskite device. And we also talking about the perovskite sensors. And this one is our research project. We try to use in the OLED concept to prepare the photodetector. So that's a vacuum deposition method to prepare the sensors. So why we try to do in this research topic? Last years, if you join the SID conference, the Samsung already mentioned that the all-in-one panel. So what's that? The OLED panel integrate or embed the sensors. So this panel can support the full screen, the recognition, like the fingerprint based on the OLED panels. So display the panel need demonstrate the sensing the functions. So how to process this? You should follow the OLED process. So what's that? The vacuum deposition method. Okay, so right now for my industry projects, we can use in the OLED concept to prepare the organic the photodetector. And this one is our new project from the Taiwan. So we try to demonstrate the eco-driver watch. So you know the eco-driver watch, we want to talk about the energy capacity. So even the indoor light, we can absorb the weak light and convert become to the electricity to charging the microelectronic. So if you want to do in this, maybe you can demonstrate this transparent solar cells. So that's my second part of the talk. I want to share our design rule or the working experience for you. And I hope our participants, you can get the more and more knowledge based on our the presentation. Okay. Okay. So if you want to study this pure research, or you want to the service of companies, supposedly for our centers we need to build up the core facility, right? So this slide we just briefly show you what is the core facility we have. So the first one slide we show you the measurement assistance. For example, we have the time without the PLO and the SEN with the index functions. We also have the photo response platforms. That's for the sensors, the measurement. And we have the time of flight, impedance, atomic force microscopy, the EQ, the surface profiles, and the Raman assistance and the integrated spheres. Anyway, we have the two, the commercialized assistance. One is a KP, and another one is a Pyros, the measurement assistance. So that's a commercialized the measurement assistance. And for the fabrication assistance, I think that maybe like Professor Matsushima also have this the assistance. So we have the Globus, the photo lithography assistance, the laser, the pattern, the assistance, the thermal evaporator or the sputtering the assistance. So we have the many type of the purified assistance and the two type of the cleaners. The one is the CO2, and another one is the O2 plasma the cleaners. And we have the huge one, the commercialized starlight coaters for the perovskite solar modules. And we have a two-state, the different type of the atomic layer, the deposition. And we have the CVD, the pairing the coaters, and the perovskite, the deposition systems. So that's a popular, very commercialized or the popular the machines for our members. Anyway, for my teams, we need to take in the industry projects. So always we need to service the companies. So in our teams, we need to build up this integration, the fabrication systems. That's a huge one assistance. So in my design rule, I like using the low bar, and this low bar can rotate to the forward position. So the two position for the thermal evaporator chambers, and the one position for this O2 plasma treatment, and for the backside position, we can connect this grow bus. And the two grow bus can connect together. And for the grow bus, the left side we can mount the ALD, and this side we also can mount another one, the thermal evaporator chambers. So because we have this the huge one, the fabrication systems, so we can prepare the high quality organic or the perovskite, the electronic, and without any emolument degradation. So that's our the older one, the integration fabrication systems. And this one is our the new one, the industry project systems. So we try to make the two grow bars connected together. And this time we try to install the non-linear flow to improving our emolument the qualities. And for the this size, we can mount the ALD, and for the grow bars base size, we also can mount the two the thermal evaporator chambers. And for these chambers, actually we can load in more than 9 organic materials. And for these chambers, that's very special chamber. We have the E-gang the source, means that we can try to deposit the metal or the metal oxide. So this chamber just for the keeping layer, and we can demonstrate the transparency of the solar cells. So in the talk, so I will show you what's our achievement in these research fields. Okay, so now you can briefly understand what is a core facility we have in my centers, and we try to explain and introduce our previous work in the organic or the perovskite fields. So the first one, the talk, I want to explain what is the images, and you need to understand how to prepare the individual the components, right? For example, like a display, sensors, or the transparency electrode, right? So I will focus on this research topic, and then you know what is our achievement in these fields. Okay, so the first one part, I want to talk about the OLED applications, but I want to make the special things in Taiwan. Actually, the cultural difference, we cannot compete to the Korea or the China, because in Taiwan, we don't have the OLED, I mean, bigger one, the OLED company, right? So if you are the researcher and you say that I want to study the OLED, I'm sorry that you cannot get the project. So we need to change your slogan. Always I will say that we try to study the medical or the lightweight OLED applications. So what's that? More recently, we can demonstrate the servable, the product, the concept, that's demo key. For example, we can demonstrate the electron patch, the hair goes in the comb, the hair pins or the putty mask, or the circadian the glasses. And for our the cooperation of the projects, we can make so many specialty materials, like we have a different color emitter from the deep blue or the cyan, green, yellow, orange, or the deep red, the different type of emitter. We can synthesize and demonstrate this emitter with a very nice the device performance. And we also finding This cyan color is very specialty. If you can try to excite the human retina, the melanocyte systems, maybe you can change it or modify the melatonin distribution. So what is the benefit for that? We can change it or improving your sleeping quality. So the next slide, we will show you how can we transfer our knowledge become to the final product. Because I already mentioned that if you want to work in our university, you need to demonstrate your contribution. So how to transfer your pure concept become to the final product, then you need to sort out. So that is our vision in our university. Otherwise, you cannot survive in our university. And we also can looking for the different type of applications for the OLED. So for my industry project, we can demonstrate the highly transparent the OLED the device, the panels, and we also can demonstrate this crumble, the OLED devices, and we can put this crumble device on the bubble, and that times you can see that we can turn on this very lightweight OLED and without any problem, because we know that how to protect our crumpled device. So it means that we try to take more time to study the packaging, the method for that. So I want to demonstrate the demonstrations to prove that our concept like this. We already turn on our device, and we can put this device into the water and without any problems, because we have a simple persuasion to protect our device without any problems, even we drop this device into the water. So we don't worry about the involvement of the issues to degrade our device performance. So supposedly you should have very nice the packaging method to protect the organic electronic. If you can doing these things, maybe you can make something special things if you want to do, okay? And we want to demonstrate how to transfer our knowledge become to the OLED therapy. So like I say, every morning you just need to wear out the OLED, the therapy for the 30 minutes. We can wake up your mind. We also can improving your sleeping quality. So we are not always talking about the pure research. We want to know how to find the particular application based on your knowledge, your know-how, and we need to transfer your concept become to the final product. Okay, so let me show you what's that. So like this, every morning you just need to wait 30 minutes, and we can emit the cyan color, right, to control the melanocyte, the distribution. So that's very important if you want to improve the sleeping quality for the peoples, or you want to enhance your concentration ability to improve your working efficiency. So we're talking about the healthcare, the concept. So we are not only talking about the OLED. We want to find the particular applications because we are the engineer. So we need to publish a good paper, of course, but how to transfer your good paper become to the money, okay? So that's another one story, okay? So we are the private university and we want to make something special things because we are the researcher, okay? So we also co-work with the companies and we can demonstrate our concept can work, okay? So that's my vision for these centers. And we also talking about the pure research, okay? So we have one team, we try to study the perovskite, the light emitting diode. So until now, we have two systems for the near-infrared emission. The one system, we try to synthesize the bulk, the perovskite systems. Another one, we can synthesize the perovskite quantum dot emitter for the LED. And we can get a very nice device performance. For example, for our near-infrared emission, the EQ already higher than the 15% at maybe the 772 nanometer. But unfortunately, I need to talk to you, that's a pure research. Because for the perovskite LED, maybe the fabrication, the method is quite simple, right? That's a solution process or inkjet printing. But if you want to compare the device stability for the OLED, that's the bigger difference. So for the perovskite, the LED, that's very nice, the research topic, but you need to focus on how to improve in the device stability. Otherwise, you need to think about how to become to the final product. That's a big challenge, the bottleneck for the perovskite, the LED. But for the pure research, I can talk to you, that's a very nice the research topic in our teams, even in the world, okay? And we also try to make the specialty, the sensors, that's all Bakerman deposition methods. I need to explain why always we want to talk about the Bakerman process, the deposition methods, why always we want to mention this. Think about it for the OLED, already become to the mass the product for the TV, the cell phone, or the sound panels, right? So what is the process for that? That's a Bakerman deposition the method. If you want to transfer your knowledge to the company, at least you need to fit the same thinking. I mean, vacuum deposition method. Okay, so right now we want to make the small molecule, the sensors, but based on the vacuum deposition methods. I mean, we need to fit the OLED process. Otherwise, your recipe cannot transfer to the OLED factory. Impossible, because the fabrication method is different. So we study the OLED as a long time. We try to use in the OLED concept, looking for the sensors and the perovskite the devices. So that's our special things. Okay. So we know how to make a solution process. Of course, for the papers, totally fine, but for the product, cannot, because you cannot fit the OLED, the factory, the requirement. So that's the different things. If you want to take in the industry project from the OLED company, you need to fit the OLED thinking. You need to fit the OLED factory, the requirement. Okay. So we want to study the sensors, and we try to demonstrate the all-in-one panel, right? OLED combined with the photodetector. So we need to fit the OLED requirement, the OLED thinking. So right now for my teams, we can demonstrate the UV, the sensors, and this one is the near-infrared sensors, and we also have a visible light sensors. And the last years we published one papers that's a non-foreign acceptor for the small molecule, the active layer. So it means that we don't need the capacity. We just choose very simplify the organic materials, and we can demonstrate the visible light sensors. Okay, so this one, the sensors, the sensitivity similar to the silicon in the visible region. So what is important things we can do? The fingerprint or optical sensor. So the OLED can emit the green light. We need to cover the green light only. So we can demonstrate that one sensors prepared on the glass, but the performance is similar to the silicon. So that's a benefit for the organic the photodetector, because we can combine the concept into the OLED the panels. So that's an all-in-one panel. Okay. So all-in-one panel means that one panel you should have the OLED, the display, the unit, and the sensors. So we can fit the OLED process to make this all-in-one panel. So that's very important in the working the concept. But if we want to publish the papers, of course, this quality is not so good. But if we want to take in the industry project, that's very nice. Okay. And this topic, we try to talk about the different thinking for the solar energy. I know that so many people, they'll try to the process of polymer, the solar cells, or the perovskite solar cells. But in my teams, we want to talk about different story. That is the lightweight, the organic sensors. So we want to demonstrate the solar skin. So what's that? The lightweight the solar cell or the modules. And we try to change the performance, because we try to talk about the watt per grain. So watt per grain, what's that? How many power you can generate? How about your electronic, the total weight? So that is a watt per grain. I mean, this unit. And we try to demonstrate very specially and simplify the fabrication methods. That is a peeling process. So what's that? We show a photo in here. We can continue the finish out the polymer the solar cells, including your simple pasteurization. Then we can peeling out to get this freestanding the electronic, and can put it on your arm. So this device, the total weight is quite small. Okay, so we can show you this the demonstration videos. You can easily catch my point. We already finished this whole the device structures. Okay, then we can peeling out to get our lightweight the solar cells. Okay, and this solar cells is totally weight below the 1 milligram. So in the future, if we can make the lightweight the solar modules, we can demonstrate the solar skin. We want to drive in the aircraft. So you know the airplane, the weight is very important, right? So we need to talk about the watt per grain. So can you drive in the airplane without any the power, battery? Only the solar skin can support this project. So if you can demonstrate the solar skin and to drive in your airplane, if we have a light, then your airplane can fly. That is a hot topic from the NASA. So that is the future. So we don't like to study the rich, the solar cells. We want to study very specially the lightweight, the solar skin. So what is the challenge for that? Device stability. So you can check that these device structures. We have the aluminum oxide, the ALD, the simple pasteurization process, and we make the sandwich the structures. It means that we can coat in the aluminum oxide on the bottom and the top side. So that's the sandwich structures. So for this device, we can under the one sun, more than 2 days, we still can maintain the T80, the device performance. So that's very nice, the device performance for the solar skin, okay? And right now for our concept, we can get the 45 watt per grain, okay? So if you want to demonstrate the images, I say that you need to understand the components, right? Display, source cells, or detector, or transparency electrode. I want to introduce simplify the method to pattern the transparency source cells. Okay, so I will call that, this one is a laser pattern, the methodology for the source cells. In general case, we will prepare the perovskite source cells or the polymer source cells, and we have the sintered electrode. So that is an opaque electrode. So if you know how to use in the triple one laser to cutting your working area, supposedly you can demonstrate the transparency source cells. So that's a very simplified thinking. But how to process this, I can talk to you. So if you can use in the laser to cutting the working area, of course we can allow the light to pass through your media. So the thinking is very simple. So I think that I can make it especially the shape. So that is the hexagon shape. So once we increase in this width of the hexagon, the shapes from the small size to the bigger one size, we can quickly improve in your transmission value from the 13.6 to the 15 to the 16.5%. I mean transmission value. So if you can make the huge one, the width of the hexagon, the shape, we can allow more light to pass through your media. Means that we can improving your transmission value for standard one, the source cells. Okay, so that's very simplified concept. So we also can demonstrate this the transparent source cells, and we never changing the color purity. Okay, so that's a very interesting research topic. But what is the important things for that? We need the buffer layers. With the buffer layers, we can improve our process yields more than maybe 85% compared to the without the buffer layers. This yield is below the 15%. So it means that we can get a very smooth the corner, the shape like this. Okay, so that's the simplified concept how to make the transparency electrode. So in my teams, we have so many the methodology to prepare the transparency the electrode. The one is a laser pattern the method to make especially the patterns. The second one, we can design the multi-layers to increase in the transmission, the properties, okay? So this slide, we just briefly introduce what is my thinkings to make this simplified transparency source cells. Okay, so now we already prepare as well, because at least I can handle the three components, right? Transparency electrode, and the photodetector or the sensors, and the display the unit. Always we choose the OLED, right? So how to integrate these three components into the single electronic, that is a challenge. So to start out the images, maybe we can check this reference paper. That's very nice, because we can get a lot of the knowledge from this reference paper. So long time ago, maybe the research teams, they'll publish one paper to the applied physics data, and they'll try to use in the continuum process to integrate the two units. So they'll want to combine this quantum wave and the light emitting diode in together. So which means that this quantum wave, the photodetector, that can absorb the UV, the light, not the UV light, sorry, the IR, the photons, then dissociate these photons become to the free carrier. And we try to study the electronic. So always we will apply the electric field for this electronic. So we can easily push this the free carrier going to the light emitting diode to recombine and generate the yield emission. So if you check this one, I mean this electronic, you can find in this device can absorb the IR, the photon, then show you the near infrared rate emission. So if we check this electronic overall energy, that is a go up and not a go down. Okay, so we can define that this electronic using the up conversion process. But I need to mention that when talking about the electronic up conversion process, we never talking about the single molecule, the up conversion, the process. That's a complete different things. Okay, so that times I read this reference paper, I think that wow, that's very nice. But I also find some drawback for these things. They'll try to choose or select the inorganic the materials. So that means that always your same thing need to deposit on the silicon or the sapphire, and you need the high temperature of the process to cooling your inorganic materials, right? So how can you process your image on the flexible substrates or transparent glass? No way. So in my mind, I think that maybe I can follow this working concept. but I try to change in the material type from the inorganic become to the all organic materials. Okay, so that's why I continue working in this field more than 10 years, because I think that we can demonstrate a very high impact in the image sensing the field. Okay, so that's our contribution in this field. And I try to explain what is our knowledge to demonstrate the organic images. So images, you need to combine with absorption and the emission, the functions, and your electro need to demonstrate the transparency type. Okay, so that's very basically the requirement for the images, because we want to demonstrate the functional, the electronic. Okay, so what is the contribution in this field? We want to show you what is the real-time the image mapping based on our proposed images. So this time we just prepare our organic images. So that's a semi-transparency electro, and we study the electronic, right? So we need to apply the electrical field for that. So you can check here. We need to provide the power for that. We try to demonstrate the real-time image mapping, right? So we put the shadow mask and the near-infrared light source. We put it in the base size, and right now I try to prove that what is our image mapping the properties. So you can check that we can turn off light first. So once we move this near-infrared light source, you can see that our images panel can show you the dynamic imagery like the movie. But we just apply the electrical field. We are not connect the driver IC, but actually our panel can show you the real-time image mapping. So we detect the long wavelengths, but finally we show you the visible light. So that's the up-conversion process. So we can prove that how to use in the organic images, and we can detect the invisible light. Finally, we can show you the green the emission. So that's the up-conversion efficiency. Okay, sorry, that's up-conversion process. We detect the long wavelengths, invisible light, but finally you can see this green the emission. Okay, so if you try to study these images, the field, at least you should understand the several the parameters. I mean, how to measure or get this important in the parameters, because we want to talk about the up-conversion efficiency, right? In general case, if you want to publish papers, you should check the four important in the parameters. The first one is the current density and the current gain ratio, luminous, and up-conversion efficiency. And for the current gain ratio, how to get this? That's very simplified, the measurement method. You just need to scan your dark current and the light current density. And these two curves, the gain, the difference, that's your current gain ratio, when shows in here. If you want to improve in your current gain ratio, how can you do? You can try to suppress or reduce your dark current density, because we study the photo detector, I mean sensors, right? You need to reduce your dark current density, means that you can get the high current gain ratio. That's a very simple concept for the images. But what is important things for the images? How many the luminous you can generate? Okay, so we need to sweep this luminous versus a voltage curve. So this measurement method similar to the OLED. So we just sweep the BV curve, right? Brightness versus voltage. But the one difference is you need to pump in the bias light to your images, because we study the sensors. So for this measurement, we choose the near-infrared light source, and the wavelength at the 780 nanometer, and the power density below the 1 milliwatt per cent square. We need to compare to the previous work. So always we need to fit our pumping the wavelengths, I mean bias light. So if we have a bias light pump to your images, actually you can get the very nice the luminous. So at the 3 volt, our images can show you the 1,000 nits. So that times you know how about the brightness come from the images, and how about the pumping the wavelengths for that, right? So you can easily to calculate this up conversion efficiency. So that's just the input and the output of the problems. So you can calculate the photon to photon, the up conversion efficiency. But I need to mention that if you try to focus on the pure research, then you pump in the 1 milliwatt per cent square for your images, I can tell you, you cannot find the particular applications. What's going on? In the ambient condition, no any signal, the light intensity higher than the 1 milliwatt per cent square. But if you just focus on the pure research for the papers, always your bias light need 1 milliwatt per cent square over 100 milliwatt per cent square. But for the particular applications, the noise background, how much? Only 1 microwatt per cent square. So that's 1,000 times the difference for the pure research and the particular applications. So we need to solve this big problem. So in our the research, always we try to using our proposed images to detect very weak the BIOS light. For example, 1 microwatt per cent square. So in this slides, I will teach you how to demonstrate this the concept based on our images, the thinking. Okay. And why is it important things for that? This slide is quite important because we need to talking about how to design your device, the structures. Okay, so basically we can list 3 types of the device configuration for the images. And we focus on this field as long time, and we publish so many papers in this, how to design the device configurations. So in general case, we have 3 types, the images, the device. The first one I call, that is an electron rigid type. So for the images, you should have the knowledge. Device including the 3 components, transparency electrode, right? That's the first one. The second one is the display unit. And the third one, you should have the sensing, the medians. So I call that as a charge junction layer. So from this electron rigid type, if we apply the electrical field for that, right? We can allow the electron inject into the images. But at that time, we don't have any in the whole carrier. What's going on? Because if we are not sense the outside the signal, the charge junction layer need to block the whole injection from this interfacial the layers. But if we can sense the outside the near-infrared the BIOS, the charge junction layer need to dissociate this signal become to the free carrier. And please remember that we always apply this electrical field. So we can push this whole carrier going to the OLED, the device unit to recombine and show you the luminance. So that's our working principle. If we can accept this design rule, electron rich the type, maybe we also can demonstrate the type 2, the whole rich the device. So that times we just need to changing this carrier flow direction. Okay, so we put our charge junction layer on the top electron side. And this layer also need to perform the same behavior. The block the electron injection if we are not sense the outside the signal. But if we can sense the outside the signals, this layer also need to dissociate the signal that become to the free carriers. And we study the electronic, right? So always we have this BIOS. So that times we can allow this electron carrier going to the display unit to recombine and generate the phenomena. So that's very basically a concept for the electron rich and the whole rich, the images, the device, the configuration. But sometimes the people today will complain, oh, Professor, your proposed device, the up conversion efficiency is not so high, right? So we need to demonstrate the final one, the tandem device structures. If you try to study OLED, you can get the knowledge. The charge junction layer can easily combine the 2, the display unit together, right? So that times this CGO can dissociate the edge don't become to the free the carrier, hole and the electron the carriers, right? And we also keep this electrical field. So means that we can allow this hole and the electron carrier going to the bottom and the top of the display unit to emit the 2 photon density. So until now, I want to mention that only in the tandem structures you can get the double the device performance. Compared to the electron rich and the hole rich the type. The images. Why? Because you have a 2 the display unit, right? So that's the different things. So if you want to improve your up conversion efficiency, you should consider the different type of the tandem device because you have a 2 the display unit. Supposedly you can get the more and more. The high the emission the properties. Okay. So until now, maybe you can briefly understand how to measure the device important in the parameters, right? Because we already mentioned that you need to check how many the luminance you can emit, right? And how to design your device structures. And we know that we have 3 types of the device structures: electron rich, hole rich, and the tandem device structures. But always, maybe the students will challenge me, Professor, I know that how to design the images, and I also understand how to measure this important in the parameters. But I still cannot understand why we need to waste the resources and the time to study the images. Okay, so the next slide I want to explain what is the benefit for that. Why we need to take more time to study the images, right? Okay, so this slide we just briefly show you the working the range from the 600 to the 1.1 the micrometer. This is a working reference range. In this range, we can separate the four the potential applications. We can talking about the security, the biomedical, the communication, and the light vision systems. We know that for the blood vessel has a very strong the near-infrared absorption coefficient, right? So if your proposed images can absorb a near-infrared wavelengths, that is the best solution for the biomedical applications. But if you can try to modify this absorption range from the near-infrared to the 1 micrometer, maybe that twice you can talking about the communication, the application. But if you can continue the enhance or the shifting this absorption range from the 1 micrometer to the 1.6 micrometer, that time you can talk about the light vision over the see-through image. But the more important thing is that if you can try to find the specific the materials that can cover the 940 nanometer, we can prepare the anti-surveillance device to monitor or detect the Face ID signal, because that is an invisible light. So that times we can talk about the security. I mean, how to protect your privacy. That's very important. So this slide, I want to mention that for the images application, that is non-limited. If you can looking for the new absorber to cover specific absorption range, you can easily find the specialty or unique the application field. Okay, I can give you some example for you. Okay, in 2015, the Frankiso group they'll propose that maybe the images can integrate into the lens module. So that time they can use in this the standard one, the visible, the CMOS sensor to take in the IR image. Come on, we know that for the IR camera, that's very expensive, right? So you can use in the standard one, the CMOS sensor combined with the images, then you can take in the IR image. And for these studies, the authors try to compare these two, the images, and you can track these two photos, and we want to know where is your cancer tissues. But unfortunately, we know that these images are taken by the IR, the camera, but we cannot easily define where is your cancer tissues. But you can try to take the same photo and combine with our images, and at that time, these images can show you very clear the result. I mean, we can easily recognize what is the difference between the cancer and the normal tissues. And most importantly, we also can combine the different pumping the wavelengths from the visible light to the near-infrared, the light source. For the long wavelengths, we know that the long wavelengths can perform the high penetration the dips, right? If you can try to change in your pumping the wavelengths from the visible light to the near-infrared light source, we can step by step to check your object, the cross-section, the profile. So this process seems to be the image fusion concept for the bioimage, the applications, right? And we can directly absorb the blood vessel from your human arm. And at the same time, we can take the PPG from your human arm. So that times, if you know how to prepare the images, we can talk about the healthcare. So this the previous work I want to mention that for the images application, that's non-limited. So just depends on which one, the absorption or absorber you have, then you can propose the very unique the applications. For example, like the bioimagery, the sensors. Okay, so the long time ago in my teams, we also can demonstrate how to absorb the blood vessel, because we know that the blood vessel have a very strong the absorption coefficient in the near-infrared range, right? So how to demonstrate this the blood vessel, the real-time the image mapping, the concept. Our the images can combine with the standard one, the CMOS sensor, and you pump in the near-infrared to your human arm, and you can directly absorb the blood vessel. That times the blood vessel will become to the dark field. This TV is not so clear, but this is you can absorb this dark pattern. Okay, so if we give me the pressure, the blood vessel disappear, but once the wind release, you can see this dark pattern again. So that's your blood vessel, and we demonstrate the near-infrared the image mapping for the blood vessel, and based on our the image concept. But in this times, I don't want to talk about this the achievement, or I mean our result. I want to talk about how to use in our images concept to protect your privacy. Okay, that's very important, because I know the one important issues for the human vision. Okay, we only can absorb the visible the light. So the working range from the 380 to the 750 nanometer only. If our vision is limited, how can we safeguard our privacy? How can we protect our souls against the tracking candy and the snake shots in our daily life? That's a critical problem. Can you catch what I say? If you work in your office, then I try to install the invisible camera in your office, in your home. Who can catch that? No one, because that's an invisible light. That is an invisible signal already over the human vision. No one can catch that. If you cannot looking for the invisible signal, how can you protect yourself? No way, impossible. So I think that maybe we need to demonstrate the new thinking based on the images. Okay, so I think that I want to demonstrate the new structures, I mean the images, and that's our proposed devices, the structures, including the 3 components. So we have the polymer, the active layer, the aseptic OLED, and the transparency electrode. So in our working concept, our proposed polymer, the active layer, that can cover the invisible region from the 700 to the 1,100 nanometer. We detect the signal, then we show you the green, the emission. So that's our proposed concept for the new type of the images. And I also can talk to you this fabrication, the process is very simple for this the proposed device structures. So if our fabrication method is quite simple, maybe we can try to prepare the huge one, the working the area for our proposed images. So our proposed device, the working area more than 9 centimeter squares. And we also can try to compare to the commercialized the solid IR card. So this time we try to measure the result based on the luminous versus the power density. And you can see that I'm so surprised that because we just in the microwatt per cent square, we can turn on our images. And that's a very important thing because we have the 1,000 times higher than the commercial IR card. If you want to purchase the IR card from the solid company, you need to pay the $50. But for our proposed device, the fabrication cost within the $5. So I think that that's very the high potential, the concept in the image senses. If we're talking about the IR card, you can see that we can show you the semi-transparent properties, and we also have high the sensitivity for the IR. This working range, and more interesting, our concept can embed it into your glasses. So how to protect your privacy. In the future, even the iPhone try to take a photo from you. Your glasses can emit the green emission to remind maybe strange uncle try to take a photo from you, okay? And our proposal, the glass can directly absorb the Face ID, the signals. We know that for the Face ID, the systems including the 3 components, the near-infrared camera, the flat light, and the dotted light to identify your face feature. But right now, our proposal, the glass can modify, can sense, can detect the invisible, the signals, I mean Face ID, the signals. So we can remind the user, watch up, unknown the Face ID, the scanner try to steer your face feature. So only this way, we can support real-time image sensing. So your glasses can coating our images, then always we can remind you if we sense the invisible light in your daily life. Okay, so that's very important. We try to protect your privacy. Okay, so this time I try to prepare the demonstration videos to prove that our images concept. The first one, the videos, we want to talking about how to sense very weak, ultra low, the power density. The second videos, I want to teach you how to hold our images to looking for or finding the invisible camera in your meeting room or in your homes. Okay, so the first one, the demonstration of videos, we try to use in the iPhone, the 14 Pro, and we emit the laser dot. That's a Face ID laser dot. And we need the testing this Face ID, the signals. So that's a particular applications, okay? So then we check it out, what's that? So this one is our proposed images, right? And like I say, we can demonstrate the 9 centimeter square, the working areas. And this time we try to demonstrate how minimal the power density we can sense, okay? So like this, we already open the power, and we talk to our students increasing the measurement distance like this. So now the distance at 1.5 millimeter, the power density around the 15 microwatt per cent square. Okay, so we can catch that, right? And we continue increasing our measurement distance until to the 3.7 meter. And I can talk to you that time the power density below the 1 microwatt per cent square, like this. We still can catch this very ultra low the signal from the iPhone. So that's a particular applications. So we want to prove that our proposed images, we can embed it into your glasses in the future. And we also can sense very weak the BIOS light, even below the 1 microwatt per cent square. If you try to study the sensors, you can try to test even your photodetector. You cannot easily catch the 1 microwatt per cent square in the lab. But our median, when testing the particular applications, so even the iPhone, more than 4 meter, and our glasses, we can directly catch this invisible light and show you the green emission. So that's very important in the concept. The second one, the demonstration videos, we want to teach you how to finding the invisible camera in your daily life. Okay, so you just need to hold our proposed images. And in this meeting room, we already installed the invisible cameras. So how can we do? Very easy. You go into the free space like this and turn off light first, because the invisible light needs to activate the near-infrared light source. So it means that if your images can catch this invisible light, our images can show you very bright green emission. So images detect invisible light, then we can show you the green emission. That's our working concept. So I find this a strange clock. Then we close, and you can see that our images can show you very bright the green emission. So obvious. Then we need to confirm this signal. So we will turn off power like this, then turn on. Yes, I can catch this green emission. Means that invisible light from this strange electronic. Okay, so follow this working principle when you try to search and find in the second one the invisible camera like this. If the images show you the green emission, something wrong, because in your daily life, no any invisible light exists in your daily life. Okay, like this, so obvious. So we find in the second one, the invisible camera from this the clock. So that's a very important concept when teaching you how to use our proposed images to find in these invisible cameras. Okay, so right now you already understand why we try to study the images, and our images can directly absorb the invisible light, right? That's for sure, no any question. And at that time, maybe so many people still interested to know how about our images, the resolution, right? How tiny the device we can sense, right? That is a big challenge, because I need to talking about the image quality and how to estimate your image quality. Okay, so in the previous work, we proposed a very simplified measurement method like this. You just need to design the pattern mask, and you will notice that what is your pattern, right? So this time we design the light pair, the pattern, and we will notice that the light to light pitch. For example, like this pattern, the pitch is 10 micrometer, and you just need to compare the what is the initial the shape and your final the shape come from the images, and the difference is your distortion the problems, and you also can try to calculate your image quality. Okay, so we design this light pair the pattern for our images, and we can check out the final image from this the panel, right? So that times we can get this very clear the patterns, and these patterns the shape is similar to our target shape, and we try to measure this light to light pitch. That is a 10 micrometer, means that our image quality approach to the 1,500 PPI. But you will confuse that, Professor, are you sure that this image quality is very high? Yes, I think so. That's very nice image quality, because I can talk to you the previous work in this measurement methodology. So for that paper, the authors try to propose a hybrid, the image assistance, means that the OLED combined with the inorganic the photodetector. So they'll try to choose the indium phosphide assistance to absorb the near-infrared light source. And they'll try to looking for this small one, the space. So the size is 132 the micrometer. But finally, the OLED show you the image become to the 144 the micrometer. You see? They'll meet a big problem about the image distortion, because they'll try to choose the inorganic assistance for that. Inorganic assistance, you are not easily limiting the carrier flow, the transportation, the behavior. But in our case, we try to choose the organic materials for our photodetector. If you try to synthesize the organic materials, you will notice that for the organic layers, we can easily confine or control the carrier transporting the behaviors. If you want to the carrier, the going to the vertical axis, somehow you don't worry the horizontal light path because the mobility is quite low and different. So that's why we can get the high image quality because we choose the organic absorber for that. Understand? So that's a molecule packing the problem. And we know this, and we can control our carrier transporting the behavior. We want to prove that our concept. So I can show you our the research result. This time we want to demonstrate the tandem device, and we can check our image quality, the limit. Okay, so in the previous slide, I already mentioned that for the OLED, the thinking, the CGO can easily combine the two display units together, right? So one CGO can connect the two display units together. No any problem for that. I need to teach you how to calculate the maxima, the upconversion efficiency, the value, ideally the value without the energy loss. Okay, so how to calculate it? You need to understand how about your EQE for the sensors. So for this photodetector, we have the EQE approach to the 15%. And the one display unit, OLED, we have a 30% the EQE, but right now we have a 2 display units, means that we can get 60% the EQE, right? So finally, you can try to summarize this performance. For our design, the device structures, we have more than the 31.2% the ideal value for our images, understand? So that's very important things. Okay, so we try to the measure and confirm that how about our image qualities. So for this case, we can absorb the micrometer, the resolution. So we can try to calculate our image quality approach to the 5,000 PPI. So that's a new world record in this the research fields. So we can demonstrate a very high the resolution based on our images. So I try to summarize right now for our images, we can absorb the invisible light, right? If we can absorb invisible light, maybe we can try to using the light to pass the data. So that time we can talk about the light fight, but we try to using the invisible light. So that's the invisible light, light fight. Okay. So we prepare very specially the images and that become to the goggles. But unfortunately, in here you cannot hear this audio. So we can play the music, and actually you can hear this music because light can pass the data. So that times the images can become to the receiver. So we can get the signal from the invisible light. And we also can allow these images to absorb the invisible signals. So this goggle is so smart because we can absorb the invisible light. We also can allow the invisible light to pass the data. So we're talking about a light fight. So we can demonstrate the images can get the very specially the applications. So how many times I have? No any limited, right? Okay, that's good because I still have a second part. Okay, so in our images, actually, we already working in this field more than 10 years, like I say. So this year, in January, we also published another one of the papers to the advanced functional materials. So we want to prove that how about our fabrication method? In previous studies, I like using the vacuum diffusion method to prepare our images. Then last year, we published one paper to the Science Advance. That time we try to combine the solution process, means that we coating the polymer X layer first. Then we using the thermal diffusion method for our display unit. So that's a hybrid systems. So these papers, when talking about the old solution process, we still can make a very high quality the images. So think about, I want to mention that for our images, the fabrication method, that's non-limited. You can choose which one you like. You like the solution process, fine. You like old vacuum diffusion, the process is okay. You like combine the two, the fabrication method together, no problem. So that's very important in the concept. So our fabrication method, that's quite the flexible. You can choose which one you like. Then you can make your images. So I want to skip this slide. So what is the impact for our study? So we published a paper to the Science Advance that times, and then the natural contact with our teams. Because our teams, we are the first group, we can demonstrate the simplify and the cheap, the wearable sensors, and that can absorb the invisible light. So it means that we can prepare or design the anti-surveillance device to monitor the Face ID signal. So think about it, that is a very important thing. And we even demonstrate this concept in the Taiwan Future Technology Exhibition. So we can demonstrate how to sense the Face ID signal. So that's the goggle in the future. So we can directly absorb the invisible light. So you want to get the pass from the tunnel, or someone try to use the invisible light to steer your feature. That's impossible if you have this technology. We can 100% protect you. No any invisible light can steer your face feature, can scan your face body, because we can directly absorb the invisible signals. So that's the images, and that's our contribution, okay? So for the first one part, we already demonstrated one sensor. We can detect the invisible signals, right? What is the contribution in the future? For your retina, for your vision, we only can absorb the visible light. That's for human. In the future, we have the smart, the goggle or the glasses. If you wear these glasses, you can absorb the UV, you can absorb the visible light, you can absorb the near infrared light, even the short wave and the IR, totally okay. We try to extend the human vision. We want to break through this limit from the people's. You can looking for any signals if you want. So that's images, and that is a very important topic in Taiwan, even in the world. Or in my thinking, I will believe that. Okay, so then we move to the second part, because that's very important. For the images, we just detect invisible light. We never use this signal. For the second part, I will try to talk about the energy harvesting. What's that? We want to make the indoor sensors or the solar modules. We want to convert the ultra low light become to the electricity, because that's very important. Think about the IoT. Do you believe that IoT will goes up? Actually, IoT already goes up. What is limited for the IoT sensor? The power unit. IoT is electronic. Electronic need the power. Electronic need self-generation of power, because the capacity is very small. So we want to make the self-generation power for the IoT. So how to do these things? Maybe perovskite, the solar cells, maybe the smarter one, the energy harvesting, the devices. Anyway, we want to gain the weak light, the power become to the electricity. Okay, if you can do in this process, light can become to the power. I am not talking about the sunlight. I am talking about the indoor light. Why? Because the peoples, we stay in the indoor one day more than 20 hours. So we want to drive in the wearable electronic, because that's a marking, okay? So the first one, the demonstration videos, I want to say that this one is OLED, but I want to turn on this device without battery and the power. So who can turn on your perovskite LED or OLED without the power supply or the battery? I can, because we want to use the light to turn on your electronic. I want to talk about the energy harvesting. Okay, so let me show you. Without any power, without any battery, so light can turn on your microelectronic. So how can we do this? Because we can study the indoor, the solar cells. So that's a very special thing, because that's invisible light. So if we can absorb invisible light or the weak light power, and the converted light become to the electricity, you can drive in your microelectronic. So that's very important thinking for the wearable electronic sensors, because we want to make the self-generation power. In the future, you don't need to replace the battery for your microelectronic. Always we can gain the power from the ambient light. Okay, we want to talk about this marking, okay? So this one is a transparent OLED, that's a module, and we don't need the power because the light can become to the power. So we already programmed, but we cannot absorb anything. So we try to use the light to turn on these display panels. So you can see that, what's that? Okay, so if we have light, you can see the signal from this display panel. So light can become to the power. I already mentioned these things many times. And right now, I want to demonstrate the new type of the wearable electronic sensors. So that is an eco-driver watch. We want to demonstrate Taiwan, the first one, the eco-driver watch based on the organic electronic. So what's that? Let me talk to you. Okay, so this one is a bare glass, right? No, that's a power glass. We already prepare transparent solar cell on the glass, and that is highly transparent the properties. So that can replace your watch, the cover glass, become to the power glass. So in my idea, we allow the light to pass through your medium because we only absorb the UV and the near-infrared ray, the light, and it becomes to the electricity. So that times we can drive in your microelectronic, even a watch, and we can save the more power into your storage unit. So that's the eco-driver watch, and based on organic electronic. And I know that in Japan, you have so many companies like maybe the Seiko, Citizen, or so many the watch the companies. Before they propose the eco-driver watch, it means that the silicon solar cells combined with the watch. So what is the methodology from these companies? They'll put the solar cells in the bottom side of the watch. But in my case, we put the solar cells in the front side of the watch. So we can gain full power, the density higher than the Citizen product. So that's our contribution. We want to demonstrate how to drive in your watch in the indoor light. That's the biggest challenge. So this one is our power glass. And we put it in the indoor, the condition. So you can check the light intensity, only the 404,000 nits. And we can get the free power and to drive in your microelectronic, including your watch. So that's our contribution. So we can make the smart, the self-generation power to drive in anything, including your watch. And right now we already demonstrated two types of the watch. Let me show you. The first one is a standard one, the watch. And the second one is an electronic watch. Okay, so for this standard one watch, we want to talk about the energy harvesting concept. If your watch can put the battery or the high cap, right? You full out your cap, I mean storage unit. Your watch you can continue the run. But in the indoor condition, if you can balance your energy consumption, your watch also can continue run. You don't need to go into the outside. So let me show you this concept. So right now, the watch you cannot move because we are not full out of the cap. Under the one sun, just 1 second, your watch you can move 10 minutes. So that's energy harvesting concept. One sun, 1 second, your watch you can continue move 10 minutes. In the indoor, we can balance your consumption, means that your watch you can continue run. So we can demonstrate our concept can work. We can shifting our knowledge to the company. We can demonstrate the eco watch from our lab. And that's a traditional one watch. And we also can demonstrate the electronic type of the watch. So these times we need to combine many the functions. So we have an LCD, a touch panel, the battery, and our proposed transparency solar cells. So you can see that that's just a 5-second demonstration because that's a confidential. Okay, so we have a touch panel function, and we also show you the clock, and we can calculate how many power you can get. So for the electronic type of the watch, we can extend your operation time. So that's very new, the concept. I want to say that if you can try to absorb the indoor light source, you can get the free energy. At least for the IoT, we need self-generation power. So right now, we are already ready to transfer our knowledge in Taiwan, even in the outside. So the next slide, I want to show you how to cook the new thinking for the ProSky, the solar cells, and how to demonstrate the eco-driver watch. Okay, so for our ProSky, we go for the different thinking. We try to follow the OLED concept. Why? I already explained many times. For the OLED, the product, you can looking for so many, right? TV, cell phone, wearable, maybe the watch or rings. And if you want to display the company, always we looking for the huge, the factory. For example, like the 8th generation or 8.5 generation. So let me know how about the 6th generation and the 4th generation, the factory. No one use this small one, the factory, right? But we can, because our ProSky following the OLED concept. So we can fit the OLED factory, the process to prepare our ProSky. So we're talking about the old vacuum deposition in the ProSky, the idea. So that's a vacuum deposition in the process. Within the 30 minutes, we can finish our ProSky device, and we can get a very nice device performance. So for these structures, in one sun, we can get 70%. I know that's very poor, but I don't care about this one sun performance. I don't care about the indoor performance. So for this ProSky, for the indoor condition, we can get the 38% at the TLD 840. So we want to talk about the indoor, the applications, and what is the difference for the indoor light and the sunlight. I told you that's quite different. We only check the visible region. You can check these two figures. I want to mention that a very important concept for the perovskite, the solar modules. For the one sun, if you only counting the visible region, what is the difference for the one sun and the indoor light source? Do you know? Two difference. The first one, the light spectrum is quite different. For the one sun, always lies a broadband. But for indoor, this one is for reasons, the lamp lights a peak of the profile. And the second thing is the light intensity quite different. If you only counting the visible region, light is 15 times the difference. Means that in the one sun, you can get a very high the power density. So how about the indoor? The power density is quite weak. But that's a big challenge because we're talking about how to gain the ambient light and then become to the electricity because we try to drive in your IoT, right? So only the perovskite is the medium, we can get a very high the performance. So that's why we choose the perovskite. We are not choose the organic the solar cells. In the indoor condition for the perovskite, always we can get a very high the power conversion efficiency. So that's a big challenge and that's a very important thinking. But what is a challenge for the perovskite process? I can tell you the cooling the process time. Even you process the solution over the bakerman, for the standard one, the cooling the process, we need 15 minutes for your cooling the process. That is a take time impossible for the factory. So we propose the cooling the method. That's intense the thinner the light. So in my case, in the ambient condition, only 2 minutes we can finish our the cooling the process. So we can improve our the perovskite, the crystallinity, and we also can get a very nice the stability. So for our the bakerman deposition the perovskite, under the one sun aging, more than 1 month, we can get the T90 for our the power conversion efficiency. So that's why, because we get a very high the crystallinity for our perovskite when using the intense thinner the treatment, we just need 10 minutes, 2 minutes, then we can finish the process. I mean the cooling process. But for our deposition the process, we just need half hours. We can finish organic perovskite and electro. So that's very critical fabrication methods, and we can transfer this knowledge to the OLED company. So that's our future research plan. We want to cook this the concept for our watch. I mean eco-driver watch. Okay, so because at this time we have a time limit. Okay, so I just briefly introduce to the research topic in my centers. The first one, we demonstrate the images, and I want to say that for our new project in Taiwan, we want to looking for the short wavelength IR the applications. For our papers, always we're talking about the Face ID the signal. So the Face ID signal at 940 nanometer, but we want to demonstrate maybe WAP. So that's a 1.6 the micrometer. So that's a big challenge. So we're looking for the new absorbers, maybe the working the range around 1.3 to the 1.6 the micrometer. So that's our new project in Taiwan. And for the energy harvesting, like I say, we try to demonstrate the perovskite, the fabrication methods. So we have the different thinkings. For example, we try to demonstrate the cold deposition methods, or we have the two-step the fabrication methods. So what's that? We can finish our inorganic perovskite first. Then we change in the chamber to form the perovskite because we need the organic the perovskite the precursor to doing some the chemical reactions. So that's a different thinkings. So that's our the energy harvesting the concept. Okay, so I want to thank our center members. Actually, this time I just given the two the research topic because I mentioned that our vacuum deposition organic and the perovskite electronic, and we also show you what is our medical lighting, including our organic images. Actually, we have so many different research projects from our centers. For example, like the Yuqing Huang, he handled the perovskite, the solar cells, and the modules. So I am not talking about this result at this time. And the Professor Su, actually, she taking the bioelectronic and the sensings. And Professor Zheng, he can synthesize the perovskite quantum dot for the LED. And another one, the two the members, the Professor Li and the Professor Liu, he can make very specially the optical the integration the systems, or we can talk about the cells. Oh, that's really cool the applications. Our paper already accepted this week. We can use in the perovskite the same thing combined with the ultra thin the metals, and we can induce the source, the mechanism or the phenomenon. Means that we can try to detect the specific the object. For example, like the pesticide, the BTD from the juice or from the food. So the perovskite, the same thing is we are not looking for the solar energy. We also looking for the especially the sensor for your food or for your juice. So that's a really cool applications. So maybe next time, if I have a chance, the Professor Watanabe invited me to give another one of the talks, I can try to share his or her the research topic. Anyway, thanks for your attention. I take a long time, maybe okay, the 70 minutes. Okay. Okay, so I think that if you have any questions, you can try to ask me. If I know that how to give me a good suggestion or answer, I will doing my best knowledge to provide the useful knowledge for you. Okay. If you have any questions for the images or the energy diversity.
Thank you very much. So every time you talk me over the brilliant talk, and also every time you update how to your research to transfer to the commercialization. Yeah, I really enjoy it. Okay, so now open to the question or comment from this audience, and also if from online, if you have, in this case, could you please use the raise hand button or directly type your question and comments. I'm sorry, I need to keep the online, so
Okay.
but I keep this structure. Okay, okay, Professor Gao, please.
Thank you very much.
Yeah.
Thank you very much for your very nice talk, and there are many new ideas to me.
Yeah.
So because I'm also working on perovskite, so I'm very interested in the second part of your talk.
Yeah.
So of course I have many questions, and because of time I will select two very general questions.
Okay.
So first question is that because you already developed the applications of perovskite very close to human beings, like
Yes.
perovskite skin, and also the indoor application.
Yeah.
And I want to ask what is the policy of light toxicity in Taiwan? Because I know in many countries like Europe, it's very strictly restricted of the use of lead. So what is the policy in Taiwan? This is my first question. And the second question is that, of course, I believe the application of indoor is very useful for the IoT. And but for the commercialization attempt in the worldwide, like in China, in Japan, or Europe countries, most companies are focusing on the solar panels.
Yeah.
And also the flexible solar panels, and also the building integrated application.
BIPV.
The special companies for the indoor application is very limited.
Yeah.
What do you think about the reasons? Like one possible might be the market size, or other comments. What do you think? This is my question.
Okay. Okay. Yeah. Very sense. Your questions. Of course, that's very general case. And if you talking about the privacy, I should talk to you. Like my case, because I work in a private university, so always we have a funding from our group. So our policy only one rule. We need to deliver our concept for our group. Yeah, so that's a policy. But of course, we also can take in some of the projects from the different company or from the government. So we just depends on who provide the research funding for our teams. We have so many channels can get the funding. For example, from the government. And for another one, the companies or from our groups. So, but always we under our group. So maybe more than 80% of fundings, in my case, just get from the group. So always we need to deliver our patents or the transfer our knowledge to our group first. But if our group don't want this technology, of course we can looking for the different part. I mean different company, or we ask the government funding to support this very important in the project. So who provides the funding for our teams? That's a policy. So they can take out like this. And if you're talking about the applications, that's very important in the concept I can explain, because last 2 months I also come to the China, and of course so many people they are looking for the solar panel, because that's very easy things for the people to understand what is your contribution. So they want to ask the funding. That's all. they are not serious to worry about the perovskite's futures, because how many times you need to deliver your product, and even you demonstrate the perovskite solar modules, right? How about your sold price? And if you want to talk about the tandem device structures, that's very nice, the topic. But you need to solve your lifetime the problems, because I also come to the Korea, they're giving me the same the comment for this tandem the structures, because if you want to combine with the CIGS or the silicon, do you know the lifetime for that? More than 20 years under the one sun. So how about perovskite? So that is a challenge. And you need to make a large scale. But how about your sold price? So if you want to talking about the particular applications, one issues, how about your cost? How about your marketing? Okay, so if you ask me the suggestion, I will talk to you. Okay, why we looking for the wearable electronic? Do you know? Because for the solar panel, maybe the big one, the panel, the sold price maybe $20 US. But for the wearable, the sensors, you also can sell the $20 US. So sensors, for example, the visible light sensors, or you make the self-generated power for the IoT, maybe you can get more the benefit. I mean, based on the perovskite, the concept. And why is a big challenge for the perovskite? In my thinking, for the OLED, you already can use this the final product, right? So for the OLED, they'll just maybe spend 15 years from the pure research to the final product, only 10 or 15 years. But the perovskite already over the 10 years, right? So only 5 years. If you are not demonstrating the particular the product, that's a big challenge for this technology. So in my mind, we already invested so many funding to this topic. So within the 1 or 2 years, I need to demonstrate the product. So we need to follow the small one, the cheaper. That's the easy way we can demonstrate the final product. So for the wearable sensors, I mean IoT, or for the watch, that's a very easy thing for combined with the perovskite concept to deliver the final product. Otherwise, you are not easily demonstrate your solar panel. I mean, based on the perovskite the concept, because the lifetime is a big challenge, and your fabrication the cost big challenge. How can you combine with another one, silicon or CIGS? That's a big challenge. Yeah. So my comment is that finding the wearable sensors, or you can looking for the the IoT the battery. Maybe that's an easy way for the perovskite to demonstrate the final product. Okay. So I mean, you need to looking for the particular application soon. Otherwise, you cannot demonstrate this technology.
Okay, thank you very much. I just a very small question. So if this perovskite is put on top of the watch, do you think people will worry about the light in their everyday using?
Oh, I can talk to you. For the watch, because Taiwan we have a big one, the watch company, so they will so worry about your design rule. You cannot design your layout by yourself. No way. They cannot choose your concept. For the watch, they'll have so many specialty patents. So you need to demonstrate how to make the smart, how to make the specific patent for your perovskite process. So that's a big challenge. You need to solve this the problem first. For example, for the solution process, we can coat in the whole area, right? But for the watch, no way. We just need maybe very specially the patents, right? So you need to demonstrate if you want to choose the solution process for that, you can cover this requirement from the company. So that's why we choose the vacuum diffusion method, because for the OLED, we have a shadow mask, right? So we can easily make the patent for our panel. So you don't need to talking about the application. You need to talking about what is your skin. Can you make the specialty patent from your process? If you can, that's a very nice solution for the wearable sensor. Another thing is, if you want to talk about the IoT, the battery, you need to worry about your power conversion efficiency from the indoor light. So how minimum the power density you can convert the light to become to the electricity. That's a big challenge. For example, like the 600 lux, 300 lux, 15 lux. Can you get enough of the power from your perovskite? So that's a challenge. Okay, so I will recommend you think about this the special things. You can easily reach the company requirement. Okay.
Thank you very much.
Okay, thank you very much. Any other questions or comments? From audience or also not. So
Okay.
I have a simple question. Simple question. In this case, you are successfully using the in biomedical, you say.
Yeah.
And also your glasses is NIR can be changing, transfer to the green light.
Yeah.
So very surprising.
Yeah.
So my question is, in this case, you are using the organic molecule.
Yeah.
Sometimes NIR or IR can be also receive heat energy.
Yeah.
So this means heat energy can be changing the morphology or stability of the organic molecule. So I'd
Yeah.
like to know your durability issue. So if you,
yes,
if you measure, yeah, just simply.
Yeah, that's the particular the problems. But anyway, we have the sensing media in the front side. So always the signal already absorbed from the sensing layers for the display the unit without any problems for that. So always when we are doing this UV the edging to confirm that our device the stability. So we have the new the papers right now we just prepared the drift. Actually, we also can use in the images, and we can make like a surface plasma, the resonance, so we can detect the maybe bias or like the COVID. So we don't need the computing, and we don't need any assistance. We just need to drop the test the samples, and then we can make the patterns for our images. So now we looking for how to demonstrate our concept of become to define on the product, because in our centers we need to demonstrate the product. So fundamental of the projects, we just allow you starting maybe 1 or 2 years. Then you need to talk to me how to transfer your knowledge become to the final the product. So always our project that's a top down. So what's the top down? We already know where is the market, and we looking for this market the big problem. So that's our bottleneck. So we want to solve this bottleneck. Then we can demonstrate the product. So that's our center, the research, the loop. Okay, so now for the OLED, we're talking about the OLED therapy, so we can make the glasses. I also prepared one gift for your director. Okay, that's OLED therapy. And for the energy harvesting, we can demonstrate the eco-driver the watch. So like this, that's our working style. But anyway, I think that if you have the time and you come to Taiwan, please let me know. I can arrange you some the agreement tool for you in our center, and then you will know many things from there. Okay.
Okay, thank you very much.
Yeah, thank you.
So if you not more question, in this case, I'd like to thanks again to present.
Yeah, thank you.
Okay, thank you very much.
Thank you for joining our the presentation. Thank you. Yeah.
Okay, thank you very much joining. So we are closing this session.